Welcome to lecture 11 of FIR filter designs using window techniques. In the previous session we have seen how to use a rectangular window to design a FIR filter. In this session we will see what are the other kinds of windows available to design the filters. Among them, first one is a triangular window. So as the picture shows here, the triangular window is such that it has a tapered sequence from the middle on either sides. Okay, so you can recall a rectangular window. Okay, and you can note down the difference. So in a rectangular window we have the sequences covering from minus m2 plus m with the equal amplitude. But now in the triangular window it is a tapering like structure and the sequence tapers starting from the middle on either sides. So here when you look at the magnitude response of the triangular window, the side lobe level. So these are the side lobes. So the side lobe levels are reduced from minus 13 to minus 25 dB when compared to the maximum value, but the main lobe width it still remains at 8 pi by n or twice that of the rectangular window having the same duration. Okay, so for this actually illustrates that there is always a trade-off between main lobe width and the side lobe. Okay, so this is the main lobe width and these are all the side lobes, and this is particularly representing for the filter length equal to 31. Now this triangular window, it produces a smoother magnitude response for the FIR filter design. Okay, so here figure D shows the magnitude response of low pass filter which is approximated using triangular windows. So here we can see that the characteristics almost closer to the ideal response, and the side lobe. Okay, so whatever the magnitude of response is there in the stop band. Okay, so it is at the least or the minimum levels. Okay. So that's why the triangular windows, they produce a smoother magnitude response in case of FIR filters. And also the transition from pass band to stop band, okay, it is not that much steep when compared to the filter design using the rectangular windows. Okay, so this is a transition band. So this transition band is not that steep when compared to rectangular windows. And in the stop band, of course, the response is smooth, but the attenuation is less than that is produced by rectangular windows. Okay, so therefore in comparison with the rectangular window, so what we observe here is, first of all, the transition is not that much steep, and also the attenuation in the stop band. Okay, so it is less when compared to the attenuation produced by the rectangular windows. Okay. Similarly, next we have another type of window, that is Hanning window. Okay, so in Hanning window, it's a log magnitude response. Okay, it shows that the first side lobe is minus 31 dB relative to the maximum value. Okay, and also here an improvement of around 6 dB is obtained when compared to the triangular window. So therefore when compared to triangular window, okay, the main lobe width is same, but the magnitude of side lobes is reduced. Okay, so therefore this Hanning window is preferred when compared to the triangular window because of this feature. And also you just observe the figure D here. What it shows, it's the magnitude response of low pass filter approximation which is done using the Hanning windows. Okay, so here we can see some ripples are there, as well as you can see the stop band features. So they are slightly different from that of the previous window. So we can say that the magnitude response of LPF designed by using this Hanning window as shown in figure D. Okay, so what we have to note in this is an improved stop band attenuation characteristics. Okay, and also here it is given that the largest peak is approximately around 44 dB relative to the pass band levels. Okay. So these are the characteristics of the Hanning window functions. Similar to this, we have one more, that is Hamming window. Here, coming to this main lobe features, okay, the magnitude of first side lobe, it's been reduced to minus 41 dB. Here you can see that. Okay, so the magnitude of these side lobes is reduced to minus 41 dB, and here an improvement over 10 dB relative to the Hanning window is seen. But this improvement is done at the cost of the side lobe magnitudes are remaining constant at the higher frequencies. Okay, so this is visible that whatever the side lobes are there, so their magnitude is remaining constant. Okay, so as frequency is increased. But whereas in case of Hanning windows, okay, the side lobe amplitudes, see here you can observe, in case of Hanning windows, the side lobe amplitudes are going to gradually reduce with the frequency. Whereas in case of Hamming window, the side lobe amplitude is going to remain constant. So therefore, what is its effect on the low pass filter designed using this Hamming window? Okay, so that is visible here. So just take a look at the previous window, that is LPF designed using the Hanning window. So it has ripples in the pass band, as well as you can see the attenuation characteristics in the stop band. Just in comparison with that, here we can see some smooth variations even in the pass band as well as the stop band. Okay. So it is noted that the first side lobe peak is here at around minus 51 dB. Okay, so which is less when compared to the Hanning windows. But as the frequency increases, okay, the stop band attenuation does not increase. Okay, so when compared to the Hanning window. Okay, so this is what is the important characteristics. Okay, so this stop band attenuation, okay, so this will not increase with the increase in the frequency. But you just compare this with the Hanning window design. So here we can see the attenuation features. Okay, so the amplitude is slightly increasing, but here the stop band attenuation characteristics are good when compared to the Hanning window. Okay. Next we'll go to another type of windows, that is Blackman window. So the Blackman window sequence you can see, and this is again plotted for the filter length 31. And here the Blackman window width, that is the main lobe width, is 12 pi by n. Later we have a list of all the features, and this width is the highest among all the windows. And also the magnitude of the first side lobe, okay, so magnitude of the first side lobe is minus 58 dB, and here important thing to note is the side lobe magnitude gradually decreases with the frequency. Okay, so this feature is achieved, okay, so at the cost of increased main lobe width. So even though main lobe width increases, the result is here the magnitudes of the side lobe, it gradually decreases with the frequency. Okay, so therefore always there is a trade-off between the main lobe width as well as the characteristics of these side lobes. So the main lobe width here is, however, it is reduced by increasing the value of m, that is here we have taken 31, for 31 it is plotted. Okay, so this width can be still reduced by increasing this value. So the figure D, it shows the characteristics log magnitude response of FIR low pass filter, which is designed using the Blackman window features. Okay, so here also you can see how this transitions are there in the stop band. Okay, so these are the features of the Blackman window. Now coming to this Kaiser window. Okay, so here the window function will be basically a mathematical problem. Okay, so mathematical problem of finding a time limited function. Okay, and whose Fourier transform is best approximated as a band limited function. So here coming with respect to this Kaiser windows, as you can see the Kaiser window sequence as well as the log magnitude response of the Kaiser windows. The main feature is that it has a parameter beta which controls the degree of taper towards the edge of the windows. Okay, so that is here with respect to Kaiser windows we have a shaping parameter. Okay, so because of which so it is possible in order to shape a particular window function, and also the designer can achieve a better trade-off between the main lobe width and the side lobe performances. Okay. So these are some of the windows that are used in the design of FIR filters. So here this table shows a consolidated list of all the windows and their window functions. Okay, and this table it shows the important frequency domain characteristics of some important window functions. So for rectangular window, the width of the main lobe is 4 pi by m, and also the peak side lobe in decibels it is minus 13 dB. So similarly for other windows we have the main lobes as well as their side lobe magnitudes. So therefore in case of design problems where we are asked to choose a proper window function, okay, so for the given specification, like we need to design FIR filter with the side lobe around minus 30 dB, then choose a proper window function. That's the problem. So in such problems, depending on the given side lobe value, so you can choose a corresponding window, either Hamming, okay, so whichever is closer to the given values, so that main lobe width and the corresponding the window function can be chosen. Okay, so this is a some brief discussion about the different types of windows and their important frequency domain characteristics. Thank you.